Welcome to the DCU LightComm ECONET Demo 3. This demo is on the frequency scaled router with dynamic local control policy implemented in software. In all of our work, we use the NetFPGA 1G board. It was designed in Stanford, and details can be found on the netfpga.org website. We use this board because it's open source and low cost reconfigurable hardware. On the board, two SRAMs work synchronously with the core logic, and this can be toggled between 125 MHz and 62.5 MHz using a register. The board provides four 1 gigabit per second ECONET ports. These can be interfaced both to the external and to the host operating system. The board can be optimized as a number of devices. In our case, we use a version that's optimized as a high-speed networking router. We use the reference router project, which can be found on the NetFPGA website, as a base for our work. We use a second board optimized as a network packet generator. In our work, we found that dynamically toggling the frequency between 125 MHz and 62.5 MHz on the reference router causes a board reset. This reset causes all buffered packets to be lost. We designed a new NetFPGA 1G frequency scaled router instead. This eliminates the board reset problems, and we also introduced three more frequency options. So now there are 5 operating frequency options for more finely tuned frequency switching. The frequencies that we have now are 125 MHz, 83.3 MHz, 62.5 MHz, 50 MHz, and 41.7 MHz. The frequency change on the new NetFPGA 1G frequency scaled router occurs on the core Vertex 2 FPGA chip only, but not on the SRAMs or on the physical ports, which still run at 125 MHz. As mentioned previously, we implemented a basic local control policy in software for dynamic frequency scaling based on traffic load. This is a picture of our lab setup for the demo. You can see the packet generator, the network router, and the power data acquisition unit. The packets are sent from the packet generator, from the 4 ports on the packet generator, routed through the router, and back to different ports on the packet generator.
This is a snapshot of our actual lab setup. Our lab setup consists of 2 NetFPGA 1G boards. The first one is here, inside this case. The first NetFPGA 1G card is configured as NetFPGA packet generator using standard Stanford NetFPGA packet generator project. And this packet generator is able to send packets at any required bit rate. Now we can see from this packet generator side that how the packet generator works. From this monitor, we can see that we can specify the packet numbers, the pcap files, and the bit rate. So in this case, we can see that 4 ports are sending traffic at 586 megabit per second, and the transmission duration is 2097 seconds. Now let's move on to the second NetFPGA 1G board. The second NetFPGA 1G board is here, configured as our DCU frequency scaled router. This board is an open source and low cost reconfigurable hardware, optimized as a high-speed networking router. And this board provides 4 1 gigabit per second external network interface to the host machine operating system. And we can see here in the middle part, it is a NetFPGA vertex 2 Pro. And on the left hand side is 2 SRAMs. And now we can see that the LED is blinking because they are receiving packets. It's just working normally as a network interface card. And let's take a look at the frequency scale router. First, we see the score grid. From score grid, we can calculate how many packets received, how many packets sent and dropped for each queues. In this case, we can see that there is no packet dropped. Okay, on the left hand side, it is our dynamic frequency scale router script. From this script, we can see how many packets received from each port per second and the current frequency the router is working on. In this case, the frequency is working on 125 MHz. Now we take a look at the power consumption tools. The tool we used to measure power consumption of NetPG1G board are PCI bus extender plus a data acquisition unit. This PCI bus extender can precisely measure power consumption of NetPG1G board while it's working by connecting these 3 pins: white 3.3 voltage pin, white 5 voltage pin, and black ground pins to the data acquisition unit. As we can see here, we connect these 3 cables from the PCI bus extender to the data acquisition unit. In this case, we use the LabJack UC6 as our data acquisition unit. And National Instruments or oscilloscope can be used as this data acquisition unit as well. The data can be automatically saved and collected to this desktop by connecting this USB cable, as we can see here. And a software LabVIEW is running on this laptop to show us the current of the power consumption. We can see from the upper curve, it shows us the power consumption of 5 voltage components of this NetPG1G board. The lower curve is showing us the current of 3.3 voltage components of NetPG1G board. And the total power consumption can be calculated from these 2 values. Okay, this is a brief introduction of our lab setup. Our frequency scale router is implemented in software, and the local control policy is based on 2 aspects. The first is the total packets in received queues from Q0 to Q3, combined with historic results for the worst case scenario with the smallest 60-byte packets. And the second is packet losses. If there is any packet loss, and we will increase frequency by 1 level. Now, let's take a look at how our frequency scheduler works. Now I'm going to run these 5 packet generator scripts one by one and show you how our frequency route works. First, let's run the test case 1. Okay, from the test case 1, we can see that is one port on and transmitting 500 megabit per second traffic. Okay, let's check from the rotor side. Okay, from the rotor side, we can see one port is receiving packets, and the rotor can still handle traffic loads like this. Only one port, 500 megabit per second. Now we can check from the power consumption side. We can see the power goes up because there is more traffic involved for 20 seconds. Okay, let's run the test case 2. Okay, the test case 2 is 2 ports on, and for each port is 430 megabit per second. And now let's check from the rotor side. Okay, we can see that 2 ports are receiving packets, and now the frequency is changing from 41.7 MHz to 50 MHz because the rotor cannot handle the traffic like this, so its frequency goes up. And now we can see that the power consumption is higher than previous one because there is more traffic involved and the rotor is working on higher frequency. And now let's run the test case 3. Okay, we can see that test case 3 is 4 ports on. For each port is 387 megabit per second traffic. And we can see from the rotor side, okay, the 4 ports are all receiving packets, and the frequency is changing from the 41.7 to the 62.5 MHz. And we can see that the power consumption working on the 62.5 MHz is higher than the 50 MHz, higher than the previous one. Okay, let's run the test case 4. The test case 4 is 3 ports on. For each port is 460 megabit per second traffic. And we can see from the rotor side, the 3 ports are all receiving packets, and the frequency is changing from the baseline, which is 41.7 MHz, to the 83.3 MHz. And now we can see the power consumption consumes more than the 62.5 MHz because more traffic involved, and the logic is working on the higher frequency. And now we run the test case 5. The test case 5 is 4 ports on, and for each port is 586 megabit per second traffic. Okay, from the rotor side, we can see that the 4 ports are all receiving packets, and then the frequency is changing from 41.7 to 125 MHz, which is the highest frequency the rotor provides. Okay, we can see that this is the highest power consumption than all the 4 former ones. Okay, this is a short demo of our frequency router.
The net FPGA router results. We found that each operational frequency has an associated traffic throughput threshold, beyond which the router will begin to lose a significant number of packets. For our results, we found that the number of ports turned on makes a difference, and you can see our publications here. The temperature also makes a difference, and you can see some of our publications on this here, and the packet size makes a difference. Our hardware changes introduced in the frequency scale router make a difference. The changes included added asynchronous queues between the clock frequency domains, and this has increased the delay and power consumption. And also we wait to finish processing the current packet before switching, again increasing our delay and power consumption. But as it stands, the board is a good proof of concept and shows the advantage of multiple frequencies for scaling based on traffic load, and it also avoids the reset at each frequency change. It facilitates tests on dynamic local control policies. The DCU team is currently looking at reducing these delays.
Here is a summary of our frequency scaled router experiment results. This figure shows the aggregate traffic load handling capacity of the scaled router for different frequencies and different packet sizes. From this figure, we can see that larger packet sizes have less header processing per byte of payload, and so have higher throughput, up to around 3.8 gigabit per second. Small 60-byte packets at 125 MHz reach around 1.9 gigabit per second. Higher frequency corresponding to higher capacity for same packet size. For example, for 1500 byte packets, the throughput is around 1.3 gigabit per second at 41.7 MHz, compared to around 3.8 gigabit per second at 125 MHz. Now, this figure shows the comparison of power consumption for the frequency scaled router running at different frequencies and the original reference router, where the hardware code used as an overhead caused by the asynchronous FIFO introduced between the input arbiter and the SRAMs. The new design allows more refined frequency operation for different loads. The frequency scaled router can work at lower frequencies, so it will result in overall power saving, although at the same working frequency it consumes more power than the reference router. Thank you for watching DCU LightComm ECONET Demo 3.